and welcome to the Nerd Life. I'm Jonathan, and I'll be talking about some physics and its relation to the movie Romeo and Juliet. Not really, but I'll cover basic calculus and kinematics, and we'll have some fun along the way. So first, I'm going to talk about the strange problem that we're going to solve. First of all, I found this problem from my physics textbook, Physics for Scientists and Engineers, 3rd edition by Douglas C. Giancolai. It's from chapter 3 of the textbook, and it is listed under general problems. It's not a very challenging problem, and AP Physics 1 students could solve it simply using algebra. However, because I promised I would teach some calculus sometime on this channel, I decided to get some of it over with right now by talking about derivatives and integrals. So, first off, what is a derivative? Well, what is a derivative, I ask? Well, a derivative is basically the change of something over time, like a slope, at a specific point of a function. And it's this change in time or distance between these 2 points that is infinitesimally or really, really small. That's what it means. So this can be represented by this equation. It's called the difference quotient. And what you can use it for is taking a limit as h approaches 0, and that means the distance between the function is so small, it's basically 0. So it's this difference minus the actual function. And basically when you're finding derivative, you're finding this equation that represents a slope. So you're finding basically the slope of a curve at a point. That's what a derivative is. So basically one example would be 2x. Let's say I plug in 2x to a difference quotient. And here, f of x equals 2x. So limit 0 to x plus h minus 2x over, 2x over h, 2x plus 2h minus 2x over h cancel, and it leaves us with 2. And that's the derivative. 2 is the derivative. And that's how you find a derivative of 2x. Now, that's the slope of the line at any point. And basically what that means is if I graph this 2x function, f of x equals 2x, if I graph that, it's going to look something like this. And basically the slope of this line at any point on the function, it's going to be 2. It's going to be 2. You don't trust me? Well, try it out yourself. It's always going to be 2. Same slope along this straight line. Now you can do the same process with other functions, but it'll still work. And one would probably realize after doing a lot of work with a difference quotient that you could derive some rules. So here are the rules. If you have a constant, so the derivative of a constant is 0. It's always 0. Like 5, the derivative of 5 is 0. If you have a constant and a variable, so let's say a x, then, well, it's going to be that constant. If you have a constant and a variable raised to some power, let's say ax to the third, what you're going to do is you're going to take that exponent, put it in the front as a coefficient, a times x, and then you're going to subtract 1, and it's going to be here. So that's what it's going to look like. Basically, if you have a function 5x squared, you would take that, so 2 times 5 times x, then you subtract 1 from the exponent, and that gives you 1, so it would be 10x. So those are some rules that you can actually use without having to do the difference quotient every single time. And that's the derivative, the slope of a curve at a point. And there's more to calculus than just derivatives. Actually, introductory calculus at most courses, and in AP Calculus AB, include integrals. So instead of finding slope, integrals are meant to find the area under a curve. So basically the integral, this is how you'd say it, the integral from a to b of this function dx equals something. This is the definite integral from a to b along this function. So let's say you have, I don't know, a parabola. And you want to find the area from here to here. You would put in the function, and you would say a to b x squared dx. And you would solve it, and you would find basically this area here under the curve. So that's how you would do it, and that's the graphical representation. Now, integrals are kind of the reverse of derivatives. They're sort of like the inverse operation. So basically you could say integral of this is that, derivative of this is that. So they're sort of like the inverse operations of each other. Now, basically, what we can say is we can do sort of like that rule that I showed you earlier with the exponents. Here it's called the power rule. We do that in the reverse. It's called the reverse power rule, obviously. And basically, if you have an integral like this indefinite integral 3x dx, how would you do this? Well, it's the reverse of the power rule. Remember the power rule? You're going like 5x to the fourth. You take that here, subtract 1. So you would give, would be 20x to the third. Well, this one is you add 1 to the exponent, so it would be 3x squared, and then you take that and you divide instead of adding. So it would be that plus c, which is some constant, and I already went over why it's some constant. So that would be basically the indefinite integral of this, and that's pretty cool. So those are integrals, and these are derivatives, and they're both really cool and useful in physics, because derivatives can help us figure out, well, the velocity of something if you have the position. And basically, by definition, velocity is how position is changing. And that's the derivative. That's what the derivative is defined as. It's the change of something. It's the slope of a curve at a point. So anyway, let's analyze this problem for Romeo and Juliet. Now, Romeo is chucking pebbles gently up to Juliet's window, and he wants the pebbles to hit the window with only horizontal component of velocity. He's standing at the edge of a rose garden 8 meters below her window and 9 meters from the base of the wall. How fast are the pebbles going when they hit her window? So basically, we want to find how fast these pebbles are moving, we want to find their velocity, and we're given these heights and the distance from the window, and Romeo's here and he's throwing the pebble here. How fast are the pebbles going when they hit her window? So basically we want to find velocity of the pebbles. And that is our Romeo example. Okay, so basically the scene doesn't actually happen in the film.
Nor arm, nor face, nor any other part belonging to a man.
My ears have not yet drunk 100 words.
Oh, Romeo, Romeo. Wherefore art thou, Romeo?
But anyway, there are some things that we do need to know before we solve this problem. It's the derivative of the position is velocity, and by definition, the derivative of this is the velocity. And you can represent that with this notation, the Leibniz notation. And the derivative of the velocity is the acceleration, and by definition, and you can signify that with equals sign. And just basically by definition, the derivative of the position is velocity, and derivative of the velocity is the acceleration. So that's all you need to know right now. And what I'm going to do now is I'm going to derive a bunch of equations that you need to know for kinematics. And all those equations basically come from this, plus some basic intuition. So I'm going to do that. I'm going to go through it really fast, and then you can look over it and do the algebra in your head if you want, but I'm just going to do like a really informal proof, so don't worry about this. So basically, here are these 4 kinematic equations, and there's one more, but I'm not including it. And anyway, these are all used to solve these problems, And here, I'm just going to go through it really quickly, actually, just so I can explain this calculus part that you don't really need to know, but it's helpful because you'll learn it anyway. And this is called the differential equation, and what you could do is separate these variables. The way it works is really hand-wavy, and it's a really complicated proof that, honestly, I myself have not really learned. But basically, throughout calculus, you're going to do things that you don't completely understand, and it's still going to work. So we treat this Leibniz notation as sort of like an algebraic expression, and we move this dt over here, and we take the integral of both sides, thus giving us this, and that gives us our main kinematic equations, which we can derive these two from. So basically, using that intuition, I'm going to do another informal proof to find these very specific horizontal and vertical components for kinematic equations. So I'm going to do that here on the side. And basically, you can find these by basic intuition. They make sense because here it's the velocity of the horizontal component times t. And if you go back here, you can see that, well, it's like this. Except, obviously, when you're throwing something off of a cliff, or you're throwing something horizontally, there is no initial horizontal velocity. Here you're just dropping it, and it's in free fall. And for this one, it's always going to be the same no matter what. It doesn't accelerate. The velocity doesn't change throughout the path in free fall. When it's going in the horizontal direction, that's just a fact. And these ones, they're just like the y component versions, and they don't mean much. And by the way, if you don't know what this symbol means, the not symbol, that just means initial. And when I don't write a symbol at all, then it just means final. So some people use this, some people use this. I don't really care. It makes no difference to me. So basically, 1, 2, 3, 4, 5, 6, 7, 8, 9. So these 9 equations are going to help us a lot, and we're going to use almost all of them, but mainly these ones, when we're solving our problem. And you'll be using these a lot throughout physics. Okay, so one more thing. This, g, that's the acceleration of objects as they fall towards the Earth. And it's really like around 9.8 meters per second squared. But on the AP Physics C and the AP Physics 1 and AP Physics 2 exam, they're okay with you using g equals 10 meters. Okay, so yeah, we have 8 meters in this direction, and we have 9 meters. He's 9 meters from this. And basically, here's the window. Here he is, Romeo throwing his pebble. Yeah, and it's going in this path. And it says that when it gets to here, there's no velocity in the vertical direction because it's only a horizontal component. It says that. So we can assume that it's at its maximum point in a parabola. When it reaches this point, it's not going any higher. It's only going to the right. It's only having a horizontal component. So with that information, we can use this equation. Vy equals v naught y minus gt. And we know that this equals 0 because vy equals 0 at this point. So v naught y minus gt equals 0. And we want to solve for time because we're going to need that later. We always need that. And that's an unknown. We only have this height. We only have this. So it's good to know. And we're going to say gt equals v naught y and t equals v naught y over g. Now we don't know this. We don't know this at all. But we can work with this, okay? We can work with this. And what we're going to do now is we're going to sort of find basically how high it's going, how it's changing, and we're going to write that equation out right now and see where we go from there. So here we have this change in y equals this v naught y t minus 1/2 gt squared. And right there, we can see that we can actually plug in some equations. And we know that gt equals v naught y. So we can actually use this and put it in here. And we're deriving this equation ourselves, and that's pretty impressive. So here, y equals gt squared, because it's times another t, minus 1/2 gt squared. And that's just 1/2 gt squared equals a change in y. And boom, we can solve for t since we know g. So this is amazing. Gt squared equals 2y. And then we could cross that g here, take the square root to find t. And basically t equals 2 times the height over g. And what is that, you ask? Well, we get our handy dandy TI-84 plus CE calculator out here, and we figure this out. So 2 times the change in y is actually 8 meters, so 2 times 8, and divide by 10. That's 1.6, take the square root, and our time here. I'm going to use all the significant figures, because you know what? I don't care. So time is equal to 1.264911064 seconds. So that's time. Now, let's solve for this. What's this? What's that, you ask? Well, let's write out our equation that includes this and time and nothing else. X equals, well, v naught x t, right? And we also know that v naught x equals vx because it doesn't change over time. So using both these equations, we can find it, plug that in, solve. X over t equals v naught x equals vx. And what's x? Well, it says it's 9 meters, so we're going to trust that. Over 1.264911064. Love those significant figures. And what's the answer? Well, 9 divided by 1.264911064. I could have just used the answer button, but it's okay. It's 7.115124736. And you know what? Just one significant figure. I don't care anymore. It's 7 meters per second. Wow, and that's our answer. That's the speed of the pebble when it hits the window. Isn't that amazing? And it only took about a page of work. Are you proud? Actually, it took more than a page of work since we derived all these kinematic equations. Now, here's a piece of advice from your friend Jonathan. Don't ever, when you're given a problem, derive everything ahead of time, just so you can get a better grasp of it later. Practice your derivations before you do the problems. Don't do them while you're doing the problems, because that is a really bad strategy. Trust me on that. So anyway, that's how fast it's going to be going. And that's the problem. Thank you for watching this video. This wasn't really supposed to be educational or whatever, because I skimmed over an entire year of high school math. Hopefully you now have like a basic understanding of what derivatives and integrals are. I'm just going to go over that again. It's the slope of a curve at a point. That's what a derivative is. And an integral is the area of a curve at between 2 points. And there's like some rules you need to know, and like difference quotient. That'll impress your math teacher if you bring that up. And basically you're going to cover some of this in pre-calc BC at Sacred Heart. If you're in that class, if you're at Sacred Heart. And basically this is going to help you throughout calculus, throughout high school, throughout math, throughout physics, and basically throughout your life. So basically by watching this joke video, you learned calculus, you learned physics, and you're now a happier, well-educated person. So thanks for watching, and I'll see you later.